purpose of this movie is to describe Phoebus 1b and to discuss the operational aspects of attaining the reactor objectives and to emphasize the possible problems and the reactor red lines and parameter limits. Most of the material that I'm going to discuss is covered in the reactor test requirements document, which is available in Nevada from either Jim Henschel or Bert Knight. The Kiwi B4E reactor is the basis for the Phoebus 1 design, and Phoebus 1b is similar to the Kiwi B4E and Phoebus 1a, except that it is to be run at 1,500 megawatts instead of the nominal 1,000 megawatts, with some of the fuel elements approaching the Phoebus 2a power density and flow conditions. In addition, there is an important difference in the fuel elements themselves. The NRX EST and A5 test results indicated much more severe corrosion in the fuel elements than had been expected based on predictions from electrical testing. In addition, hot gas tests at Los Alamos on the Phoebus 1b elements of the type used in A5 and EST indicated a severe mid-range corrosion problem when the higher powers and flows of Phoebus 1b were used in the tests. Fortunately, at about this time, it was found that a small amount, about 2 grams, of molybdenum metal laid down as an overcoat over the normal niobium carbide coatings in the elements, in the bore coatings, significantly decreased the mid-range corrosion. And these coatings then, the molybdenum overcoats, were applied to Phoebus 1b fuel elements after the entire core had been fabricated. While we were originally primarily interested in the high power and flow and some hot end support block sticking problems and cracking problems, this fuel element problem discovered on the NRX reactors has taken on additional importance, and the emphasis on the objectives of Phoebus 1b has turned more to getting corrosion information under conditions approaching the Phoebus 2a conditions, which of course are the conditions we ultimately hope to attain for flight reactors. The objectives then of the reactor are as follows. Primary objectives are to operate the reactor at 1,500 megawatts with a fuel element exit gas temperature of 4,500 degrees R to provide this environment that I spoke of. To operate at full power in a single cycle for 30 minutes or until a predetermined amount of control rod motion has taken place, to obtain information on the fuel element bore and external corrosion, the effectiveness of several design options in reducing the corrosion at the core periphery, the fuel element hot end and support block corrosion. And another objective is to obtain experience on local exit gas temperature measurements for monitoring temperatures at the core edge to permit operating Phoebus 1c at an average fuel element exit temperature of 5,000 degrees, which is of course 500 degrees higher than the present reactor. Secondary objectives are to obtain performance characteristics of 6 tie tube clusters of the type used in Phoebus 2a, to operate the reactor without a neutronics power loop, to perform some controls experiments, to obtain experience with the new neutronic measurement system required by the Phoebus 1b 360-degree shield, and to obtain experience with the large 110 mil bore fuel elements of the type used in Phoebus 2a. Would like now to give a brief description of the reactor. The basic building block of the reactor is the fuel element cluster, which consists of 6 fuel elements surrounding a center element and contained and supported by a tie tube and a cluster block. This model, which I have, is foreshortened, otherwise all dimensions are correct. This 8 inches becomes 52 inches in the reactor. The sketch I have here now shows this in a little more detail, and I'll give a little rundown of what is in the cluster. The fuel elements have 19 holes, and each fuel element has a separate metering orifice. There are about 28,000 of these holes and 28,000 of these little orifices in the total reactor. The center element has a pyrographite insulating liner which protects the cooled tie tube, which comes down to here and supports the cluster at this end. The coolant for this flow comes down and dumps out and dilutes the hot gas which is coming from the fuel elements themselves. The mid-range that I spoke about, where the corrosion is the most pronounced, is at about station 20, maybe from 18 inches to 25 inches is the region of most concern for the corrosion. The support blocks are made also of graphite and completely coated by niobium carbide, as are the bores of the elements, the hot ends of the elements, and some of the outside of the elements, which I will mention later. Going now to the cross-section of the reactor, here's the nozzle down here. Here's the core. Here's a typical tie rod cluster. Here are the one of the 6 tie tube clusters which I mentioned, which are regeneratively cooled. The tie rod gas comes down and dumps. The tie tube gas comes in, comes down, turns a corner, and goes back through the center element again and dumps out and returns with the other flow. Hence, there's no dilution effect from the coolant for these tie tubes. The entire Phoebus 2A reactor will be a tie tube type. The lateral seals are shown here, and these dynamically compress the core during operation to keep it from vibrating. The reflector, which we have here, is the same type that we have had in other reactors. Now, I'd like to talk a little bit about the instrumentation. We have instrumentation at the hot end of the reactor, which I mentioned, which is new, which will measure the exit gas from the fuel elements themselves. And in addition, we have thermocouples now placed in the fuel elements themselves at station 20, which are used for the control of the reactor itself. These temperatures are averaged, and I'll discuss the temperature control business in a little more detail a little later. The next section I want to discuss is the core periphery, where we see several massive support blocks. We have to have these big support blocks to get the round shape from the basic hexagonal geometry. These have several tie tubes, tie rods, and thick filler elements out here. And on transients, reactor transients, these thick parts either heat up less rapidly or cool down less rapidly than the rest of the blocks and create a thermal stress problem which we have to watch out for and which has had some impact on our plans, as will be discussed in a little bit. We have a INVAR wrapper which prevents radial inflow, which is made in multiple sections. This is a new design for this reactor. Cooled filler strips and pyrographite insulating tile, which are full length, shown in here. Now, these exit gas thermocouples, which I mentioned, come across in an array radially, and also we have a bunch out in the periphery to get the edge peaking effect of the temperatures. The rack up on the total instrumentation then is as follows. I'll just go over this quickly to give you some idea of the type and number of instruments that we have. The primary ones I have already mentioned for the reactor control. The reactor has 37 different radial uranium loadings, and in order to flatten the temperatures, and these are the basic parameters now that we get: 1,500 megawatts, 94.5 pounds per second. Station 20 control temperatures are at 2930, which give this exit gas temperature. The dilution effect that I mentioned brings it back down to 4160 in the chamber itself. The core pressure drop is 128 pounds per square inch. The nozzle coolant tube pressure drop is 300 pounds per square inch. And the pump discharge pressure, you will see, is pretty high, higher than we've ever had before, is approaching 1,400 psi. I don't think I'll bother to go through the rest of these, but you can look them up if you are interested. I want to talk now about the run profile. There are many possible ways of starting and stopping a reactor, and we have chosen this time a profile which deliberately goes up slowly and comes down slowly in order to minimize the thermal stresses in the support blocks, which I mentioned earlier. Another requirement, of course, is that we keep the tie tubes and tie rods cool. So we have to kind of keep between these two limits in our startup and shutdown. Another feature of the run profile this time is the elimination of the closed loop on neutronic power, which allows the reactor to operate on hydrogen reactivity alone as the flow rate is increased. We have three main programmer drums to program the variables of flow rate, control rod position, and station 20. The station 20 temperatures control can override the control drum programmer within certain set limits. We have an intermediate hold at 60 pounds per second and about 600 megawatts in order to check conditions on the reactor before going up to full power. We're also using this as the maximum power for what we call the checkout run, which is given the title VP3, and that will be done about 10 days before the full power run. We'll run up to this intermediate hold and take all of our data, which we can look at and check to see that everything in the reactor is about as good as we think it should be before the final full power run. The programmer values, I have several charts here which show them, and I'll go through them just quickly for your information on general characteristics. The program flow comes up like this in about 120 seconds. Now we are discussing and probably will lengthen the time between 0 and 20 seconds. This will probably take about 100 seconds to get to this point instead of 20, as shown on this chart, in order to get the propellant line thoroughly chilled before we start on up to the high power operation. This then is the intermediate hold plateau, and the station 20 temperatures are here. The programmer asks for this value, but the prediction is that this is what we'll get because the temperature control will be in the clamp all the way up. After the intermediate hold, we will go on to the full power hold, and but before going to that, the megawatts build up just like this during this first hold, first ramp to power to there. And so you see there's a very rapid rise in power along in here, although the temperatures in the reactor will not exceed, the chamber temperature should not exceed 50 degrees per second for any part of the startup. Then going on, we're starting now at the intermediate hold, 60 pounds a second, linear ramp in flow rate on up to the full power hold of the 94.5 pounds, which we mentioned earlier. The drums now, which had been at a constant angle all this time, start now moving out to match the intermediate hold point with the full power hold point. And again, the temperatures are controlling, and so the programmed demand is slightly below the actual predicted value. This is another figure of the ramp to full power, showing the fuel exit temperature, the chamber temperature, and the station 20 temperature in going from the intermediate hold to the full power hold. The thermal power now is well behaved, very smooth all the way up to the 1500 megawatt point. After the hold, we have on the programmer drums what we call a shutdown program, which again ramps down the flow rate linearly and the station 20 temperatures linearly. Two options are shown here. In case the temperature controller is not active, we would follow this line, but we expect it to be active and come down and follow that line. Now, If everything has gone well on the test, we will perform an experiment on the way down, this is, excuse me, I'm a little ahead of myself. This just shows the control drum angles on the down ramp, and again the chamber temperature following. If we've completed the run successfully, we will perform a hydrogen reactivity experiment on the way down, which will have various amounts of hydrogen and temperature in the reactor at selected times, giving a kind of a stair step which is staggered with this is the flow which is staggered with the chamber temperature to get density changes. The control here will be to run down on the programmer a short way and then to open to stop and make a temperature adjustment by the CTO as shown here, and this lengthens the thing out considerably over the normal shutdown program. I want now to talk about the the normal and emergency shutdowns. This has been the subject of a lot of talk, work, effort, and some frustration, I think. The normal shutdown may be initiated any time when we think that it's unwise to continue the reactor operation, but there is no imminent danger. Normal means that the programmers are running at normal speed, and we may have a retreat mode if full power has not been attained, or a run mode if full power has been attained. The normal shutdowns are automated for certain conditions or may be initiated by the CTO. The program that I just showed of the shutdown is the normal shutdown program. Now, the emergency shutdown is for real emergencies, primarily for a loss of coolant. Under these conditions, we switch immediately to the high-pressure Durham flow system. The rods are scrammed, the main propellant line L11 is closed, the pump is shut down as rapidly as possible. The emergency shutdowns are automated for certain conditions or, of course, may be initiated by the CTO. The emergency shutdown system has been designed as a compromise between chamber temperature rates and tie rod temperature limits. If the chamber temperature drops too rapidly, the thermal stresses in the support blocks become too high, and on the other hand, if we don't drop rapidly enough, the tie rod temperatures will get too high. The example of this is shown right here, where for the emergency shutdown at the end of full power, the tie rod temperatures take a big jump there, although that we believe is allowable, while the chamber temperatures come down here. Now this, of course, assumes that the emergency system functions just as advertised. One other feature of the emergency shutdown system is that it is used, the high-pressure Durham system is used as a part of every normal shutdown and is initiated by the CTO late in the shutdown when we have gotten down to either about 20 or 30 pounds per second liquid hydrogen flow. Now, while we hope these emergency shutdowns are safe, they certainly are harder on the reactor than the normal shutdown, and we have worries about having emergency shutdowns followed by another full power run, particularly from the standpoint of the fuel element corrosion that I mentioned. I would like now to turn to limits and red lines, which is a pretty meaty subject, and I'll try to get through with some of our thinking and ideas on how these limits were established. We have three different kinds, really. We have the automatic emergency shutdowns, automatic normal shutdowns, a manual corrective action, which normally is a CTO-initiated normal shutdown. Now, most of the values are monitored by three core structural monitors in the TMR, which is called the crying room or the isolation ward or various names. And I have shown in the next charts just the rack up for what the panels contain. This particular one is Rod Spence's panel and has the computed exit gas temperature, the average control rod position, fuel element exit average temperature, from a selected number of fuel elements. The selected periphery fuel element temperatures, which he has a selector switch for. The selected station 20 temperatures, which he has a selector switch for. And selected station 20 peripheral temperatures in the outer clusters, again, which he has a selector switch for. In addition, he has the following cathode ray tube displays. Station 20 radial temperature line of 6 points, one ring of azimuthal temperatures at station 20, and fuel element exit radial line, 6 points, and station 20 periphery temperatures. And finally, the fuel element exit gas periphery temperatures, 10 points of these. These are selected by rod, but must be displayed by a switch on Keith Boyer's console. The next console is the bypass monitor's console. This will be Ed Brown, and I'll just go through this very quickly. This is the chamber pressure, the nozzle inlet pressure, linear power, ratio of nozzle flow to reactor flow, the ratio of reflector flow to reactor flow, the core flow, the tie tube flow to reactor flow, and the clamp band coolant flow. And these values, if they don't agree with predetermined values, will be the cause for corrective action. Final console is Vern Zigner's. This is a temperature monitoring, and this is a series of 8 nozzle temperatures on the shell to monitor nozzle shell temperatures in case the gamma heating in the nozzle is higher than predicted. This is the average tie rod exit gas temperature from about 10 tie rods, and these are individual tie tube temperatures, one for each tie tube. I believe they're not all probably hooked in working order. We lost a couple during the assembly. These are the reflector cylinder radial pressure drop, and these two are a pressure on the nozzle, what we call the purge pressure, to indicate if the nozzle tubes have been collapsed, such as we had on Kiwi B4D. This is the nozzle purge pressure bypass indicator. Now, going on to the individual inputs on which we plan to shut down, the first one here, reactor period, is a familiar one. This is the emergency shutdown chain now. The program power is a little bit different. It's similar to our old floating power, and we have a power program which simply rides above the predicted power, and if we exceed this program, the shutdown is automatic. The fixed power of 1.5 times the expected peak power, again, is a familiar one. This is a new one, the nozzle inlet or feed line pressure change. This is a loss of coolant indicator. If we have a rapid change in the feed line pressure, particularly in the down direction, indicating a loss of coolant or a big bypass, the emergency system is tripped. Going on then to the the inputs to the automatic normal shutdown chain. Average tie rod temperatures, if they exceed 1,000 degrees, we will shut down. The primary reason for this low number here is that in emergency shutdown, these will go to a higher value, and we're trying to be safe in any event, whether we have a normal shutdown or emergency shutdown. The nozzle shell purge pressure, which I mentioned, if this goes up to a high value, it indicates that tubes have blown away from the shell and that we are in trouble. The average control rod position also requires a little special attention here. If the rods move out 20 degrees from their initial position on the final run, this will indicate that we have lost carbon from the fuel elements to such an extent that we wish to shut down. This is a corrosion type limit. Now, these are the inputs now for manual action, and the recommended action is over here. The various values are shown here. This is the bypass indicator. You saw those on the bypass console. If we have 10% bypass indication, we initiate a shutdown, and it may be a normal shutdown, or we may have special action by the CTO if the bypass looks too bad. Nozzle shell temperatures, this is a gamma heating worry, not a very big worry. This is a very high number, but we've got it in just in case. Rod position spread, if the rods aren't all ganged together as they should be, we just plan to shut down. Individual station 20 temperatures, these are extreme temperature limits now and indicate peak temperatures probably at the edge of the core, which would go along with carbon loss and power peaking at the edge of the core. Reflector cylinder delta P we're not too worried about anymore, although we once were. This is a limit that's very safe. We don't expect to get there, and the same with the nozzle inlet pressure. It's a very high number, but we don't want to certainly exceed it. The average station 20 temperatures, we want them to agree with what we plan within 5%. This would primarily be a programmer error if these didn't agree, and we want to correct that if they deviate. Same with the flow rate. Average tie rod exit gas temperature, if the tie rods get up to 900 degrees, we can manually shut down, although as you saw before, if they get to 1,000, there's an automatic shutdown. If the tie tubes get to 900 degrees, the same thing. We want 3 of them above 900. The measured and calculated exit gas temperature, if we lose both signals, we'll shut down. The chamber pressure, if we lose both channels, we'll shut down. And the core temperature profiles, this is a judgment item. If we get an asymmetry indicated on the temperature profile that looks too bad, again, we will shut down. These will all be done on voice command from the, or voice information transfer from the CSM who is monitoring these. In this case, this would be Rod. Finally, we have if the calculated chamber temperature or average mixed fuel element exit temperature is over 300 degrees above the design, we'll reduce the temperature demand or shut down depending on where it is in the run and what we think is going on at that time. And the tie tube gas temperatures, again, if 3 are above 1,000, we will shut down. This applies only to the full power hold, this section here. The other list I gave applied to the entire run. Now, in summary, I'd like to say that we've done the best job we can of trying to anticipate all the problems that we can and decide on the appropriate action based on the reactor parameter monitoring plus inputs to the automatic shutdown chains which I mentioned. I hope that this brief review will give some appreciation of the considerations that have gone into the reactor test requirements document. And I want to emphasize that a successful Phoebus 1B test operation is extremely important to the rover program at this time, since it'll provide answers to these fuel element corrosion questions that are really crucial as far as comparing reactor tests to electrical hot gas tests, which we have used for development of fuel elements, and which is really the only way we know how to develop fuel elements for improved performance. And the power and flow that we're running at will give us these answers.